So what we're going to do here is we're going to have a look at these questions from the different revision sheets that I put up on Compass for you guys, and I'm going to take you through how to answer these with CAS, and we'll go through bits and pieces of them. We'll see how this all works out. Some stuff I'm still not sure about because a lot of it was from before or when I didn't teach a subject, so we'll see how it goes. But this is the first time I'm seeing these problems. Hopefully we'll be okay. So we're having a look at this. Someone goes through a tunnel that follows this this function here. So we want to be able to do these things here. So find the exact depth when x equals 0.5, the maximum depth correct to the nearest meter. We're going to determine f dash of x. We're going to determine f dash of 2. So this is the derivative. This is the derivative when x equals 2. So we'll start by defining this thing here. So we're going to define it over this domain. So whoops. Let's go to CAS. I'm going to say define f of x equals 0.01 x open brackets, let's put it in some times x times open brackets x plus 1 plus brackets times x minus 34, 3.4 given. We're going between 0 less than or equal to x, which is less than or equal to 3.4, 3.9, 3.4. Okay, so that's what we got. So we've defined our function there. We want to find the exact depth when a tunnel is 0.5 kilometers. So there's f of 0.5, and we have that there. We could probably try typing in 0, the exact depth. A bit of a worry because we've been given a bunch of decimal stuff here. We could try f of a half, f of 1 over 2. We'll still get the same thing. We could type this differently into CAS. We could define this as being 0.01 is 1 over 100, and 3.4 is 34 over 10. Now we could try it again. F of a half. There we are, negative 87 over 4,000. So that's something we could do there. Okay, what is the maximum depth of the tunnel correct to the nearest meter? So let's graph this. Let's see, the maximum depth f of x. There it is there, correct to the nearest meter. So we'll zoom in, analyze graph. No, we're going to, oh no, we can just analyze graph. Minimum. So we go from here to here. So there we have the minimum 0.085. What is this measuring? F of x, x is horizontal distance, kilometers, find the exact depth. So 0. So this is 0.085 kilometers. So I guess that makes it, what's that, 85 meters. So that's what we've got there. Now we're going to determine f dash of x. So let's go back here. Let's find the derivative, menu, calculus, derivative of x, of f, whoops, of x. And then we have our derivative. So it's 0.03 x squared. Ooh, yep, 0.048. Then we've got that there. So that's what we've been able to have there. F dash of 2. We could say derivative at a point, menu, calculus, derivative at a point, x, our value is 2. Click on OK for f of x, and there is negative 0.01. Okay, Victoria needs to use her brakes when her gradient reaches 0.05. Find the horizontal point of entry when she first needs to apply her brakes. Remember to give you an answer using exact values. So we want to find out where our gradient reaches negative 0.05. So we'll say, we'll redefine the function. So we'll define f dash of x equals the derivative. And then we'll say f dash x. So there was what we've got there. Solve where f dash of x equals negative 0.05. We're solving that for x. Tells us it happens at 0.47 kilometers. Bit of a pain because once again it asks for exact values. So let's see if we can solve that at maybe negative 5 on 100. Same thing. Let's see. Because we've given this here as being 34/10. We still set something there to decimals. Okay, let's try this again. Now let's see. Here we go. With another define f dash that. Okay, we've got that. Now we're going to say solve f dash. And there we have it. So here we have our exact answer. So where it first happens, we'd be choosing one of these, most likely to be this one here because of the domain that we defined. Let's just check f dash of x. Yep, we've got a domain there. So that's what we'll be looking at. Remember to use your answer using exact value. So it first enters a tunnel at this value. We can see that because it happened here at 0.473. That's our equivalent to that. So basically what I did here, defined a function because it's asking for exact values. I think this may be exact, but I don't know. I just worry because we've entered in decimal numbers. So I re-entered it again, changing this to 1 over 100 and this to 34 over 10, but I forgot to do the domain. So when we found the derivative, it gave us the derivative using decimals. So then I redefined the original function, except instead of 3.4, I wrote it as 34 over 10. So I did this part again, except I set that to 34 over 10. And then from there, I got a better derivative. I got a better derivative. So I've defined f dashed, so the derivative, f dashed of x, as a derivative function, and then that ended up with these exact answers. So that's what I got. There. All right, so that's what we end up with for that one there. Now, okay, so our next question. E of t. So we're going to redefine this thing. We're going to come up with a new function. We're going to rather than calling it E of t, we're going to call it E of x, just in case we have to graph this. And no, we don't, so we won't worry about that. So let's see. So we're going to say E of x. Actually, we might stop there and make another video for the next question.